All right, welcome
Can you see my
everyone.
screen?
Yes, I can.
Oh, thanks.
So welcome back to the second part of this session. And in the second part, we'll begin with Tran Hoang. And he will be talking about quantitative Marcinkiewicz theorem and CLTs, applications of spin systems and point processes. Tran?
Yeah, thank you so much for your introductions. So today I'm going to talk about my recent works with my two supervisors, Professor Đinh Tiến Cương, Professor Supercoach, and my friend Trần Mạnh Hùng. So to begin, let me introduce some notations. So in this talk, we only consider the real random variable x, and we denote by x bar the centralized random variables, capital F for its cumulative distribution functions, and psi for its characteristic functions. And we also denote by phi the CDF of the standard Gaussians and defines log positive to be maximum of log and 0. And we know that the characteristic functions is well defined for any use in the real line, but this doesn't have to be the whole complex plane. And in fact, to extend the characteristic functions to the holomorphically to the whole complex plane, we need some conditions on the distributions of the random variable x. And if it does, then it could be called an entire characteristic functions. And thus functions class is of independent interest and is received considerable attention. So in that field of studying the entire characteristic functions, there's a very classical theorem named MARCINKIEWICZ'S. It says that if size is an entire characteristic functions that is of the form exponential p for some polynomial p, then x has to then the degree of p should be smaller than 2. In other words, x has to be a Gaussian, otherwise they're going to be degenerate. So this is very interesting theorem, and we have a small observations the following. Size of the form exponential f for some entire functions f is equivalent to say that psi has no zeros on the whole complex plane. So, the characteristic functions of the form exponential p for some polynomial p's is something like, so this condition is something like the condition on the zeros of the characteristic functions. And this condition is something like about the growth rate of logarithm of size. So we can state the MARCINKIEWICZ theorem in the following. If we have some controls on the zeros of the characteristic functions and a control in the growth rate of the logarithm of that characteristic functions, then x should be very close to a Gaussian. So in order to extend the theorem of MARCINKIEWICZ, many people assume that the entire characteristic functions has a form exponential f, and they ask that what is the right conditions for the growth rate of f, such that the random variable x has to be a Gaussian. So here are some stories about these things. So in 1960, Linux conjectures that a sufficient condition is something like this. Here, mf of I is defined to be the maximum of the modulus of f on the circle of radius r. And 2 years later, Ostrovsky confirmed that the conjectures of Linux is true, and a better sufficient conditions that is the following here. And his approach using the ideas of from the Riemann-Waldron theory. Now let me introduce our main result, which can be seen as a generalizations of the classical MARCINKIEWICZ theorem. Our main result is the following. Suppose that there's a positive number r such that the characteristic functions holomorphic and doesn't vanish on this closed link. Then we can upper bound the distance of the CDF of x bar to a Gaussian by these things. So give us some controls on the distance of the between x to the Gaussian. So to see how our theorems implies the classical MARCINKIEWICZ theorems, we apply our results to the random variables x has which is defined by x bar normalized by the variance. So if we apply our theorem for these random variables, this first term here disappear. And because in the MARCINKIEWICZ theorems, we assume that the characteristic function doesn't have any zeros on the whole complex plane. So we can let R tend to infinity here, R tend to infinity. And because it's of the form exponential P for some polynomial P, so this term here is something like a polynomial in R. So to summarize, the right hand side something like the logarithm of P R over R, and let R tend to infinity. We have 0 here. So it implies that X has to be a Gaussian. So that's why our main result is something like a generalized versions of the classical MARCINKIEWICZ theorem. And it was to mention that in the proof of our main results, we just use some very basic argument in complex analysis. Here's something about the proof, but let me skip it from this moment to talk about the application. So because our main theorems give us an upper bound between the CDF of random variables to the Gaussians, so it's not surprising that our results can give a versions of CLT. To be more precise, we consider a sequence of real random variables xn's, and we define xn hat to be the normalized random variables. So now, if we assume that there are positive numbers Rn such that for Hn, the characteristic functions psi n is holomorphic and doesn't vanish on this closed link, then we can apply our main results to the random variable xn hat here to obtain this upper bound. Okay, so if we assume moreover that this limit tend to 0 when n tend to infinity, then we can deduce that xn has tend to a Gaussian, xn tend to infinity. So in other words, the sequence xn satisfies the CLT. So it's good to comment here that in our theorem, we don't require anything about the algebraic structures of the random variables here, or any about the independencies or weakly dependent of the random variables. All we require is the conditions on the zero freeness of the characteristic functions here, and some controls on the growth rate of the log of the characteristic functions. So basically, we just need to verify these two conditions to check the CLT of the sequence of random variables. Okay, so because we don't require any things about the independence or weakly dependence of the random variables, so our versions of CLT can be applied to some very strong dependent random system. For example, here, we can apply to the spin systems. So for the setting, let me introduce a model here. We let lambda to be a d-dimensional cube, and a spin configurations on lambdas is nothing. It's just for each vertex of lambda, we assign to that vertex a vector denoted by sigma x. This is a vector in Rn. And the spins sigma x here are distributed according to some measures mu naught on Rn. And we also consider the Hamiltonians given by this formula here. Here in this formula here, we have the J are the coupling constant, and H is the external magnetic field. And the probability measures on the space of all spin configurations on lambdas is proportional to this measure. Here beta is the positive numbers, which is known as the inverse temperatures. So to a crucial ingredient to apply the our CLT versions in this setting here is the Li-Yang theorem. So for our purpose, let me introduce the partition functions for the spin system. Here's this functions. This function. Okay, and we also consider the following subset of Cn, which is denoted by omega plus n, is the set of all vectors in Cn with the real part of the first component strictly bigger than the sum of the modulus of the other components. And the Li-Yang theorem states that if we assume some conditions about the measure mu naught and the coupling constant J, then the partition function here doesn't vanish whenever the external magnetic field belongs to this open subset for Hx belong to lambda. Okay, so our objects of interest to study the CLT here is the first component of the total spin, S lambda, which is given by the sums of all the first component of the spins in the spin system. Then we have the following result. S lambda here satisfies a CLT upon centering and scaling. S lambda tend to infinity, and we also have the speed of convergence at this rate. This is thanks to our versions of CLT. So to apply our version of CLT, we need to check with two conditions. The first condition is about the zero freeness of the characteristic functions, and together we have to check some limit. Okay, so for the first conditions here, it's not difficult because with a direct computation, we can show that the characteristic functions of S lambda can be written as this form. This is a quotient of two partition functions. So now, because the set omega plus n is defined by an open relation, it's by a strict inequality. So omega plus n here is an open subset in Cn. So if the modulus of U is small enough, let's say it's smaller than some positive number r lambda, then we can deduce that this vector here belongs to this open set for every x in our lambda. So this by Li-Yang theorem, we can deduce that the characteristic functions of S lambda doesn't vanish on this closed disk. And for simplicity, we can assume some conditions on the external magnetic field H to simplify the situation, so that we can assume that this is true for the same radius r for all S lambda. Okay, so now to obtain the CLT, we need to verify the limit, which is this limit here. But actually, this is not difficult because we can up about this absolute value of S lambda. By definition, is equal to this thing. And using the triangle inequality, we can up about it by some constant m times the cardinality of lambda. Here's m is just a positive constant depending only on mu naught, because most of the cases we will assume that mu naught is compactly supported. So thanks to this upper bound here, we can up about the numerator by something like the logarithm of lambda. And in this limit here, because we assume for simplicity that r lambda is constant in lambda, so we actually can move this out of the limit, and so we don't have to care about that. And we can actually lower about the variance of the random variable S lambda is low about by lambda to the power 1/2. So in total, this limit can be, this thing here can be up about by something like logarithm of lambda to the over lambda to the power 1/2. So it's going to be 10 to 0 when lambda tend to infinity. So this explains why we can have the rate of convergence at this rate. So here is so it completes the CLT for the random variable S lambda here. I also have another applications for the point processes, but maybe I don't have enough time. So let me convince you that in this testing, we also, the general ideas exactly the same, and every step are exactly the same, in the sense that we also have a formula here to check the zero freeness of the characteristic functions. And we also check this kind of limit by upper bounding the numerators and lower bounding the denominator like this. So the general ideas are exactly the same, but for each small step, we have to do it differently because it's gonna a little bit technical. So this is the end of my talk here. Thank you so much for your attention.
Thank you, San.
Yes.
Do we have any questions for San?
I have one. So one question is, so this CLT, so you have a quantitative version.
Yes.
I mean, there always existed the following idea that if you show cumulants vanish for sufficiently high order, then you get CLT, right?
Yes, yes.
So are these central limit theorems that you're saying, are you saying they were known in this weaker form before, and is the quantitative thing the new thing, or is the CLT itself new?
Actually, this kind of approach is known before, and we have some previous result about that. And the idea exactly as the same as you said, what you said. Yes.
I had another small question of detail about the model that you had. It looked like you had some n spins at each vertex, right?
Yes.
Can you show that? I mean, but it seems to factorize, so I didn't quite, or maybe I misunderstood. Yeah. No, the definition of your model. Yeah.
Here.
Yeah.
Okay.
So at each vertex, we have n different spins, is it? I mean, a multivariate spin, sort of. But
yes.
This measure seems to factorize over I, right? I mean, is sigma super I are independent? Is it?
What is independent? I'm sorry. Can you say again?
No, this sigma super I. If you look at sigma super I, just the ith components, the different components of. So they seem to factor here, right? Don't interact. Ith first coordinate and second coordinate don't seem to interact.
Yes, in the Hamiltonian, you mean that?
Yes.
Oh. Yes. I think so. This, I mean, this is just the definition of the model, and the property measure is proportional to this measure here. And
Okay. I'll ask later. I didn't fully get it, but I'll ask later. Thanks.
Okay. Yes, you're welcome.
All right. Thank you, San. So may I request Ujan to share the screen?
Yeah. Can you see it?
Yeah, thank you, Ujan. We can, all right. So we'll continue now, and this will be the last talk of today's BPS short talks. Now we have Ujan Gangopadhyay from Department of Mathematics at NUS, and he'll be talking about fluctuations of transverse increments in first passage percolation in Z2. Ujan?
Yeah. Give me a second, like for my setup. Hold on. Yeah, okay. So let me first describe the model. So we are considering the two-dimensional integer lattice, so Z2, and this 2 should be here, but anyway. And on the edges of the lattice, we have some edge weights, which are random variables. And I'm assuming that those edge weights are IID, non-negative, and continuous. So very simple setting. And also they have like a finite moment generating function. So now we are defining paths between points. So if we have like passage time between points, so if we have like 2 points U and V, then if we have a path between them, then the total passage time of that path is the sum of the weights on that path, sum of the edge weights on that path. So this is denoted by T. So T is basically T of gamma is the time taken. It's the total weight of a path. So this is just the passage time, and next we have the first passage time. So what is the first passage time? So if we take 2 points again, U and V, and then again, like there are infinitely many lattice paths between U and V. So here, like the paths are not even directed. So there are infinitely many paths, and we basically minimize, so the first passage time is the minimum passage time among all such paths between these 2 points. So is the definition clear of first passage time? So we'll denote this by T. So this is one of the notations we have to remember. All right. So yeah, and since I'm assuming that the path that the edge weights are continuous, so there is so this. Now, first of all, there is a question whether this minimum will be attained for some path, and that can be proved that it will be attained for some paths, and that path is, and then the question comes whether such path is unique, and that happens because I am assuming that the edge weights are continuous. So there is a unique path which for which we have this minimum passage time, and that's called the geodesic. So basically the geodesic is unique between any 2 points. There is a unique geodesic. And if we this is just kind of illustration what's happening. So if we take the origin, this is the origin, and take the geodesic from the origin, starting from the origin, and going to different points, and then we'll get this kind of a geodesic tree. But I mean, this geodesic tree is not important for my main theorems, but this is how the thing looks like. It's like a fluid that starts from the origin and kind of flows towards the edges, and we have this geodesics from the origin, and we have this geodesic tree. So it's kind of a fluid spreading kind of thing. So, and this is how if we simulate these things, it will look like this. So think of again fluid starting from origin, and we are looking at, this is called the weight region BT. So this is the set of vertices which can be reached from the origin within time t. So that's like the weight region in time t. So this is okay, time 0 we just have the origin, and time 70 this is how it looks like, and so on. So this is growing, the weight region is growing with time. So a natural question is what is the rate of growth of this weight region? So it turns out that it kind of grows linearly. So if we take the time it takes from the origin to n times u is any vertex, and n times u, and then scale it by n, then that has a limit which we call g. And similarly, let's define h. H is the expected passage time, and that also kind of grows linearly. So t, h, these are, so t is random, h is non-random, h is basically the expectation of t, and g is kind of like a limiting h. So t is a random metric, h is expectation of t. It's like a kind of pseudometric. It's a non-random metric or pseudometric something, and g is a norm basically. And this, so if we, so these limit shapes, when we scale them by the linear, we scale them linear, sorry, these weight regions, when we scale them linearly and they converge, we get a limit shape, and that looks like this. So this is just the, this unit ball in the norm G. So that's, so this is basically the limit of the weight regions. But the thing is, although we know that the limit shape exists, And we know some like trivial properties, like it's compact, convex, has non-empty interior, so on. But like the exact form of the limit shape is not known for any distribution. So no matter like, so the whole thing depends on the distribution of the edge weights, but we don't know anything like for no edge weight, we know like what this limit shape looks like. Like from simulation, we can have some idea, but we don't know how, like any formula for the limit shape. And it's also conjectured that this limit shape will have some curvature properties, but again, like nothing is known. So what do I mean by curvature? Basically, we have like we may have two different like two kinds of bad situation. One situation is like if we have a corner in the limit shape, so that's bad. And the other bad situation is like when we have like a flat edge kind of. So like the conjecture is that this won't happen, but again, nothing is known. Like these are probably very difficult to prove. So for my main results, I'm going to assume that like we don't have this kind of situations. So we know the limit shape exists, so that's fine, but nothing is known about the curvature. So it's going to be my assumption that the limit shape doesn't have any corner and doesn't have any like this edge kind of flat edge. Okay. Yeah. So basically we are kind of, these two are like this. Yeah. Anyway, let's move on. So that's my assumption about the limit shape. And now, so now we need to like understand there are like two different type of fluctuations. So if I consider the difference between the passage time t and its expectation, that's called a random fluctuation. That's called the random fluctuation. And then there is this difference between the h, which is the expected passage time, and the limiting norm g, and that's called a non-random fluctuation. So we're basically looking at the difference between t and g, and we're like splitting it in these two fluctuations. So these two fluctuations are like really important. So this is what is known about the random fluctuations. So in case 10 in 1993, he showed that the random fluctuations can be like at most of the order of square root, like square root of, like that's the scaling. So that's an upper bound. And then it was improved later. Sorry, there will be half here. And it took a long time to just have a logarithmic improvement, like from 1993 to 2008. So there they proved that it can be at most of the order of square root, like square root and then divided by a square root of log. So these two are upper bounds of the random fluctuation. And then as for lower bounds, we have like Kesten again, just a trivial trivial lower bound that it's bounded below by a positive constant. And then we have another logarithmic improvement to the lower bound. So as you can see, like there is a lots of like the gap between the upper bound and the lower bound is huge. So now the question is like, okay, so that is what is known about the random fluctuations. And then what do we know about the non-random fluctuation? So there the situation is this, like this is what my advisor Kenneth Alexander proved, that if we have the random fluctuations are bounded by some scale like sigma, and sigma is kind of reasonably well behaved, then it doesn't matter what exactly sigma is, but it's like behaves in some power like way. then we can prove that the non-random fluctuations can be at most of the order of sigma times log. So in particular, from case tense result, we can get that the non-random fluctuations are of this order. Now we come to like, so what is like what should be the actual order of the random fluctuations? So in first phase percolation, it's conjectured that it should be of the order of u to the like this, the exponent should be chi for some chi greater than like, but like this value of chi is dimension dependent. Now in 2 dimension, chi is conjectured to be 1/3, and that's pretty much everybody agrees on. Because it's related to like last phases percolation, other models in QUANTITATIVE universality. But for higher dimension, people are not sure what the value of chi should be. But in 2 dimension, it's pretty much like everybody believes that it should be 1/3. And there is another exponent called xi, which is the exponent for the fluctuation of the geodesic. Like if we take the geodesic from u to v, then this is the straight line joining into v, and we're asking like how far does the geodesic go typically from the line joining these 2 points. So that should be of the order of n to the xi, and these two exponents should be related by this relation chi equal to 2 xi minus. So I mean, this is related to the curvature, and like this relation that it should hold, like the heuristic is like not that difficult, but proving it is like really difficult. It was proved by Saurabh Chatterjee for first phases percolation in any dimension, assuming that the chi and xi exist. Like we don't even know if chi and xi exist, but he assumed that these 2 exponents exist in a certain sense, and then proved that this relation should hold. And another thing is that this xi should also be the exponent for the local wandering. So what do I mean by local wandering? So I mean, xi by definition is like the exponent for this gap. Like if this is n, and then xi should be like such that this gap is n to the xi. But it's like we can show that it should also be like if we take the wandering at a distance k, then this thing should also be of the order of k to the xi. So that kind of comes trivially from this thing, like doing kind of an inductive argument. So for me, this will be crucial, like that the fact that xi is also the exponent for local wandering. Okay, now what do I mean by transverse increment? So basically, I take the origin. This is the origin, and take
Ujan?
2 points. Yeah.
Your time is up.
Oh, can I have 5 more minutes?
Maybe you can just state the problem.
Yeah, like I'm not proving. I'm just stating the problem, and yeah.
Yeah, so maybe 2
Okay,
minutes.
2 minutes. Yeah, sure. Sorry. So yeah, I'm just taking the origin and take 2 points at a large distance n, such that this distance is of the order of L. And then I'm asking like what is the difference between the passage time to these 2 points from the origin. Now that like what is the like variance of that passage time? So these 2 passage time should be equal. So the should be equal kind of in the magnitude. So the difference should be close to 0. But what is like the standard deviation kind of? And that's kind of that's like heuristically it's very easy to see, because these 2 geodesics should coalesce like within a distance of L to the 1 over xi. If this, so this is L, and they should like meet at a distance L to the 1 over xi. And then these 2 branches are kind of independent. So that's why like the variance should be of the order of L to the 2 chi over xi. So yeah, that's the heuristic, and that's very easy to see. But the whole thing is kind of trying to prove it rigorously. And basically, I assume some conditions on the random fluctuation and prove that. That's basically it. Like, we don't know chi and xi exist, so I just prove that some assumptions, I just assume something on the random fluctuations and prove that it's the right thing, like 2 chi over xi, that's the actual exponent. All right, I'll stop here. Sorry.
No problem. Thank you, Ujan.
Yeah.
So we will now just thank the two speakers, Ujan and Sun. Now we can ask questions.